Welcome to this video on how to obtain numerical solutions for partial differential equations in 2 or even more spatial dimensions. By the end of this video, you will be able to solve 2D and 3D or even higher D PDEs numerically. So what do we do if there are more than 2 independent variables? So an example here is the advection equation in 2 dimensions of a mass fraction y that gets transported with a velocity u in the x direction times dy dx plus the velocity in the vertical direction in the y direction times dy dy, and that is then equal to 0. Well, all we have to do is follow the procedure, which was, first of all, discretize the spatial independent variables into a mesh and grid. Well, now in this example here, our solution domain exists in 2 dimensions, in the x and the y direction, which means that we have to make a 2-dimensional mesh. Well, let's do this in the x direction. Let's introduce m equidistant subintervals. So that means that the cell or the grid size, the mesh size in the x direction is simply delta x is equal to the length in the x direction divided by the number of equidistant subintervals m. So I'm going to chop this domain up in the x direction. Now I can calculate the coordinate of my m+1 grid points as before, right? These points are x1, x2, all the way to xm+1, and their coordinate can again be calculated as the start coordinate plus I-1 times delta x, and the I will go from 1 to m+1, or you can just use the linspace command. But now we have also a vertical direction, a y direction. And let's split that direction up into n equidistant subintervals. If we do this, then the size of each one of these subintervals, delta y, is the length in the y direction, ly, divided by uppercase n. So if I chop it up in the y direction as well, I get this regular lattice, right? All of these individual little squares or rectangles. Now, if I have n equidistant subintervals, that means I have n+1 points in the vertical direction. And let's have them, call them y1, y2, up to yn+1. Let's call those the coordinates in the y direction of those points. And I can calculate their actual coordinate value, y sub j as the start coordinate, plus j-1 times delta y, and j will go from 1 to n+1. So you'll notice that we have now 2 indices, an index I that goes into the plus x direction, and an index j that goes into the plus positive y direction. Now this also means that the solution variables are now defined on a 2-dimensional mesh. So they will need these 2 subindices to identify their position, I, j. So let's say y, the mass fraction here at this grid point, I, j, would be that blue point. I can then identify the neighboring point in the plus x direction as I+1, j, and the point in the negative x direction as I-1, j. Similarly, in the plus direction, the plus y direction, I would have I, j+1, in the minus y direction, I, j-1. And the diagonal positions would be just, for example, I+1, j+1, and so on. Now that means my y variable, this array now, it's no longer a vector, it's a 2-dimensional array, will be defined with points in the x direction from 1 to m+1, and in the y direction, the j index will be from 1 to n+1. Now the interior of those points, remember that's where we have to solve the PDE, those will then range from 2 to m in the I index, and the j index will go from 2 to n, and everything on the outside is then a boundary point that has to be set by a boundary condition. So that's step 1, discretize the spatial independent variables into a mesh and grid. And then we just follow the rest of the procedure, right? We replace these spatial partial derivatives with finite difference formulas. Now, there are two partial derivatives in the PDE itself, and we might have partial derivatives in the boundary conditions as well. Then we incorporate initial and boundary conditions, right? We set the entire interior of the 2D mesh, the values there for y, our dependent solution variable. And we have to apply the boundary conditions. Now, those boundary conditions have to be applied all the way around the domain. So it's no longer a single point to the left, a single point to the right. It's actually a boundary on the left, the bottom, the right, and the top. And then what we do is we still obtain a system of ODEs, and all we have to do is solve that system of ODEs using any of our numerical methods for solving systems of ODEs. Now, those RK methods, for example, then work not on a single point or a vector. They will work on an entire array of the solution variable y. Now, if we're in 3D or even higher dimensions, all we really need to do is add a dimension to the mesh and the variable arrays. So in 3D, instead of having a two-dimensional array, we would have a three-dimensional arrays with indices I, j, and k. And then we would incorporate the additional boundary conditions in those extra dimensions. Now, the drawback of going to these higher dimensions is that you have to bring a lot of time, because the simulations can take a very long time, because the total number of mesh points, of course, increase drastically if I add an additional dimensions. So if we go to 3D or even higher dimensions, parallel computing becomes really essential. And I encourage you to take a follow-up class on these type of topics, how to do parallel computing, because that will open you up to the world of simulations in 3D or even higher dimensions. Thank you for watching.